What is the correct stereochemical description of the relationship between these two compounds? Okay, so here's how I do a problem like this. Oh, well, first let's say this. First, we can look at these compounds. We want to make sure they have the same molecular formula, which, right, they do. It's 6-carbon ring with alcohols right next to each other, right? So they have the same number of each type of atom in there, same molecular formula. Both the O's are attached to carbons right next to each other, so they are not constitutional isomers, right? Constitutional isomers, compounds with the same molecular formula, but the bonds vary in which atoms are attached to which atoms. So it's not B. And this pen is given out. Okay, so it's not B. So what I do to determine stereochemistry is just figure out which one's R, which one's S. Determine R and S for these. So I would write this in a way that's easier for me to determine that right away as A in its carbon skeleton. So this goes above the plane of the page, above the ring, right? So we'd want that to be a wedge. This goes below, so we'd want it to be a dash. So if we draw this like a dash, and this guy here like a wedge, right, then those are the same exact compounds. Same with this guy. Let's draw this guy out again. Okay, so this guy goes below the plane of the page, and this guy goes above. Okay? So I'll actually do it on right over here, OH. Okay. And so it's good if you can visualize these right away and tell which one's which, but I find it easiest just to use tricks, identify R and S, and then we'll have our answer. So if this OH is in the front, then H is in the back. Same down here, H is in the back here. So let's see, number of priorities for this carbon. This is priority 1, this is 2, this is 3, this is 4. 4 is in the back, so we can go around this way, right, and keep it that way because our lowest priority is already in the back. So that is a left-hand turn, which is S. Okay? So this guy's S. Let's erase, well, let's use another marker. So this guy here is priority 1, priority 2, priority 3, priority 4. Okay? So we can go around the circle again from 1 to 2 to 3. So 1 to 2 to 3. And now that's a right-hand turn if you're in your car. So that's going to be an R. But let's see, H is in the front here. So we have to reverse it to S. Okay? Because our lowest priority group is in the front. So what we do, the idea behind this is that if we exchange one group, we flip the stereochemistry. So if we switch these two groups, OH and H, we would get H in front, or OH in front, H behind the ring, right? So we go through, we determine it's R, but since we exchanged one group, we changed the conformation, so it was really S to begin with. That's how that works. So let's do the same thing. This molecule, right? 1, 2, 3. H is in the front again for 4, right? And so we're doing here is a left-hand turn, but H is in the front, so we flip it back. Let me see. So we went from S as a left-hand turn to R, right? Because we could, if we exchange these two groups, we would have a left-hand turn with our lowest priority in the back. But we already switched two groups, so we changed the conformation, so it was really R to begin with. Okay, so this guy, right? 1, 2 is up here, 3, and H is in the back as our 4, right? 1, 2, 3, right? That is a right-hand turn, and our lowest priority was already in the back, so we keep right. So basically this guy is R, R, and this guy is S, S. So they're enantiomers, right? So obviously identical would be if they're the same letters. Diastereomers would be if you had maybe R, R, and S, R or something, or just one letter difference is diastereomers. Okay, so answer C.